Um, Now let us discuss the last case, which is case 4. This is just an opposite of what we have discussed in case 3. In case 3 we have seen left to right insertion and it requires double rotation, left to right right rotation. Now here right to left insertion, and here also we do double rotation of right first followed by left. Okay, now let us take this example. Now PAB. Okay, now we have to rotate this to the right first. As a result, what you may get is that B will come root, A may go here. Rotate this. So when you rotate, B will come to the root, A will go down, and then AR will be here. Okay, the insertion happens to right left insertion. Let me explain what is right and then left. With respect to P, A and then B, the insertion was happened right to left, right left insertion. So in that case the insertion can happen here or here. So this is R. In that situations we have to follow the double rotation, which is left right rotation. So the first, after applying the first rotation, B, A and then AR came here, and then B left side should be BL. Okay, this should be BL only. BR can go here. Okay, this is BR. Note down the insertion could be here or it could be here. Once this step has done, there is no change in P. So let me do the changes as such. What is this? This is whole PL. Okay, this is the resultant of first rotation in the right direction. Now we have to apply left rotation in the above level, which is P. So as a result, what we will get? B will be at the root, P can go here, and then A can come here. Now once you figure out this correctly, all will be an easy step. This is AR. Now this is BR. Okay, no changes here. PL left should be PL only. BL should goes to the right side of P. That's it. BL. So the inserted node could be here or could be here. As a resultant, the tree will become balanced. Okay, this is the last case. So case 1 and case 2 requires single rotation, whereas case 3 and 4 require double rotation. Now let us take an example in order to understand this. Now let us take this example. Let us first check the balance factor. Balance factor for all the leaf node is 0. Straight away you can fill that. And wherever there is equal number of left and right subtree, there also it is 0. Here 1 minus 2. So this is minus 1. Here it is 2 minus 3, which is minus 1. Okay. So at every node, the balance factor is maintained. Okay, so here we check 1, 1, 2. Okay, 1 minus 2 is minus 1. Now here 2, 1, 2, 3. Okay, maximum depth is the height of this tree, which is 1, 2, 3, 1, 2. Okay, 2 minus 3 is minus 1. Now this tree is an AVL tree. Now let us insert a new node. Okay, insert a node whose value is 10. Now let us take the right position where this 10 goes in this tree. Since 10 is larger than 7, we'll take right. 10 is larger than 9, we'll take right. 10 is lesser than 12, we take left. 10 is lesser than 11, we should insert to the left side of this 10. Okay, now this is the newly inserted node. Now Immediately after inserting, let us calculate the balance factor. Okay, now let us do the balance factor for this. As I said that the balance factor gets affected the path where you have inserted. Okay, so now the balance factor for this is 0 and for this is earlier 0, now it is 1. Now 2 minus 1, it is 1. Now for this 1, 2, 3, 3 minus 2, which is, no, sorry, this one is 1 and then 1, 2, 3, fine. 1 minus 3 is minus 2. Now for this node, left subtree is 1, 2, look at the right subtree, 1, 2, 3, 4, okay. So here also minus 2. Now you see the new balance factor on this path, because this is the path while you insert, this is the path that you have come. Now you take that path and then try checking that balance factor. So 0, now this is 1, this is 1, okay. This is where the balance factor violating. Now you fix that as P. Once you fix the P correctly, now you can easily figure out what is A. Okay, now this is A and now this is B. That's all. Now you see where that the new node has been inserted. The new node has been inserted with respect to P to the right of P and the left of A. Okay, so it satisfies the case for right to left insertion with respect to node P and then A. The node P, as I said, that from the bottom, when you look at on the path, the very first node from the bottom whose balance factor is violating, that is the node. You have to fix that node as P. Okay, then immediately right side is A and the left side is B. Once you point out this A, B and then P correctly, then we follow the procedure that I have discussed earlier. Now the first procedure is that you have to apply rotation. So where we have to apply the rotation, the first rotation is at, this is A, right? So let me, this is A, mark in the different, this is A, this is P and then this is B. Mark it in different. Okay, now we have to rotate. Here also double rotation required. The first rotation is rotate right, this one, and then rotate left, this P. Okay, now let us do this step by step. Now once you rotate this, okay, 11 will go to up, 11 will go to the up, 12 will come down. Okay, now you look at only this tree. Okay, 11 followed by 12 followed by 13. Okay, so I need some space here after that. Now let me slightly move, insert 10, also I may erase. So let us use the board optimized. Now let us take this 11, we are inserting, sorry, we are rotating, and then 13 will go to the right side. Now once you rotated, 10 will go to the left of B. As soon as you rotated, please follow this marking so that there will not be any mistake. This is B and this one is A. Okay, now A right side has moved here, B's left side is 10, 10 has to go to the left of B now. So 10 will go in its right position, which is BL. Okay, and once we rotated here, the remaining is remains same. So let us copy everything as such. Now node 7, let me fill 5 here and then 6 here and then 4 here. Okay, node 7 is here. Okay, now let me take a gap. Let me write this node as A. Okay, so that this is after step 1. Okay, now we have to apply one more step. What is that? Once you rotate this right, this we should rotate at the left. So now let us figure where is that P. P is here, right? This is P. Okay. Now this is your P. You have to rotate this P to the left. Okay. Now let us rotate to the left so that B will come as the root node. Now immediately you write this as B, and then A will come here. This is A. Okay. So we are rotating this left. Once it comes, you can copy 13 over here. Where that P goes? P goes to the left. So 9 will go here, 8 will go here. Okay. And then 10 is remaining. So 10 goes to right side of this. Fine. So this is done. So we can quickly point out this one is, let me take the other marker so that it will be easy to follow. Now note down B, this is B, and then this is A, and then this is P. Okay. Once we apply rotations correctly to this portion, the remaining part is untouched. Okay. So now you look at the level 5. 5 is at level 1. Okay. So let us take 5. 5 level, next is 6, then this is 4, no change, and then 7 is the root node. Okay. So you can connect that because there is no change over here, only the path where it get affected. Okay. So now you see this is opposite of the case 3 that we have discussed. Now you see that B will be the root, P will be the left side, A will be the right side. And then this one, the whole subtree is PL, and this one is AR. Okay. AR, this subtree is BL. Okay. And there is no BR. Okay. BR, if at all BR is there, it goes to the left of A. Now there is no BR. So this is the procedure. Okay. Now let us calculate the balance factor for this. After rotating, you find the balance factor for these leaf node. Everywhere it is 0, and for this also 0. This also at the same height. This also at the same height 0. Here it is -1 because there is no left child. Okay. There is no left child for 12. So 0 minus 1 is -1. Now you look at this 1, 2, 1, 2, 3. Okay. 2 minus 3, which is -1. Now it satisfies all the condition. Okay. Hence the tree become self-balanced. So this is all about cases. So when you ask to construct an AVL tree, depending on the cases, wherever the node affecting the balance factor, you immediately apply any one of the rotation according to the cases, then make the tree self-balanced, so that the height of the AVL tree in the worst case is always maintained in the logarithmic of n. Okay, that's the advantage of a self-balanced binary tree. Thank you.